Hi. In this video, we'll cover measures of statistical accuracy, which is a new category of statistics that we're covering. Let's start by talking about what a measure of statistical accuracy is. A measure of statistical accuracy is a value that a researcher calculates to measure the accuracy of a sample statistic that he or she has calculated. When a researcher calculates a sample statistic, like a sample mean or a sample proportion, to estimate an unknown population statistic, the researcher will want to get an idea of how accurate the sample statistic is likely to be. The researcher will want to get an idea of how close the sample statistic is to the unknown population statistic that he or she is trying to estimate. If the researcher calculates the measure of statistical accuracy, the measure of statistical accuracy will give the researcher an idea of how accurate the sample statistic is likely to be. There are two types of measures of statistical accuracy. One is called the standard error. One is called the margin of error, or the 95% margin of error. These values are pretty similar, but they're a little bit different, and they're interpreted differently. They actually have different meanings, and we'll go over their different meanings in this video. A standard error is a value that estimates the difference between the sample statistic and the unknown population parameter. It's an estimate of the actual distance between the sample statistic that the researcher calculated and the unknown population statistic that's being estimated. The 95% margin of error tells the researcher the distance from the unknown population parameter that he or she is trying to estimate to the lower boundary and the upper boundary of an area in which the sample statistic is likely to fall. So the 95% margin of error really tells the researcher the range in which the sample statistic is likely to fall around the population parameter. A researcher who's doing a study to estimate a population statistic doesn't have to calculate both of these. The researcher can just calculate one or the other, or the researcher could calculate both. They're really just two different options to measure the accuracy of a sample statistic. So the following is true about measures of statistical accuracy. They can only be calculated with random samples. That's because it's possible to predict the accuracy of a random sample. When a sample is randomly selected, the accuracy of the sample can be predicted based on how big the sample is and how much dispersion exists in the population. When a sample is randomly selected from a population, the sample statistic is likely to be more accurate if the sample size is larger or if the population has less spread or dispersion. However, when a sample is non-randomly selected from a population, then the accuracy of the sample is less predictable. When you take a non-random sample from a population, it's very difficult to predict the accuracy of the sample because it depends on how much bias there is in the sampling process. If a non-random sample is selected in a biased way, the sample will be biased even if it's a very big sample. So overall, when you take a random sample from a population, it's possible to predict how accurate the sample statistic is likely to be, and therefore a measure of statistical accuracy can be calculated for a random sample. Measures of statistical accuracy come out to smaller numbers in situations in which the sample statistic is likely to be more accurate. If I calculate a measure of accuracy like a standard error or a margin of error, and it comes out to a small number, that's telling me that my statistic is likely to be accurate. It's telling me that my statistic is likely to be close to the unknown statistic that I'm estimating. However, if the measure of accuracy comes out to a big number, that's telling me that my sample statistic is likely to be not very accurate. It's likely to be far off from what I'm estimating. And the third point is that the measures of accuracy, the standard error and the margin of error, come out to smaller numbers when either you're using a bigger sample size or when the population you're sampling from has less dispersion. That's because in these two situations, the sample statistic is likely to be more accurate or more on target. The sample statistic is likely to be closer to the population statistic in these two situations. So here's the formulas that are used to calculate standard errors. There's really three different situations in which you can calculate a standard error. If you're calculating a sample mean to estimate a population mean, and the population standard deviation is known, you would use this formula to get the standard error. You divide the population standard deviation, sigma, by the square root of your sample size. Let's take a moment to think about why these two values are inside of the formula. I said that the accuracy of a sample statistic depends on how much dispersion is in the population and the sample size. The population standard deviation represents the amount of dispersion in the population, and the n represents the sample size. So the two things that are affecting the accuracy of the statistic both go into the formula so that they're both taken into account. And the outcome of the formula is the standard error. Another situation in which a standard error can be calculated is when a sample mean is being calculated to estimate a population mean, and the population standard deviation is not known. When a person is calculating a sample mean to estimate a population mean, the population standard deviation is actually always unknown. The researcher never knows anything about the entire population. So this is, if you're calculating a sample mean to estimate a population mean, this is the real life situation. This is the situation that a researcher would actually be in. And this is the formula that's used in that situation. You calculate the standard deviation of your sample and divide that standard deviation by the square root of your sample size. And the standard deviation of your sample is an estimate of the unknown population standard deviation. So in this situation, you don't actually know how much dispersion is in the population, but your sample standard deviation, which measures the amount of dispersion in your sample, can help you get a rough idea of how much dispersion is in the population. Overall, you're using the sample standard deviation as a substitute for the population standard deviation. The sample standard deviation tells you how much dispersion is in your sample, and then that gives you a rough idea of how much dispersion is in the population. The third situation in which a standard error can be calculated is when a sample proportion is being calculated to estimate a population proportion. This is the formula that's used to calculate the standard error in that situation. P hat is a sample proportion, and you calculate the p hat in your sample and plug that into this formula. You multiply p hat by 1 minus p hat and divide by your sample size, and you get the square root of the answer. Also, if you're in a situation in which you're taking a random sample from the population, and the population is not 20 times larger than the sample, then an extension has to be added to each of these formulas, called the FPC. However, in a real study in which a person is estimating something about a population, the population is typically always very large. So the population is pretty much always 20 times larger than the sample, which means you don't have to worry about this extension right here. You just use these formulas. Now let's go through our first example of calculating a standard error. We'll calculate a standard error in a situation in which a person is calculating a sample mean to estimate a population mean, and the population standard deviation happens to be known. So here a person is interested in estimating the mean hours slept per night by people living in a certain city. There happens to be this many people in the city, and the person knows that the standard deviation of the sleep times in the population happens to be 2.3. The person randomly selects 5 people from the city and surveys them on how many hours of sleep they're getting per night, and these are their 5 answers. Now let's go through the question. First, we want to know what the sample mean equals. We can get the sample mean by adding the 5 answers and dividing by 5. It's 6.6. We know that this sample mean isn't exactly equal to the unknown population mean. That's because no sample is perfectly accurate. However, we want to get an idea of how accurate this sample mean is likely to be. We want to get an idea of how far off it is from the population mean, and the standard error will help us answer that question. But before we can get the standard error, we need to answer this question. Is the population 20 times larger than the sample? We can answer this question by dividing the population size by the sample size. If the answer comes out bigger than 20, then the answer is yes. The population is 20 times bigger. And it looks like the answer is yes right here. Since the population is 20 times bigger than the sample, you don't have to worry about that FPC. You don't have to worry about the extension to the formula. We can just use the short formula. So this is the formula that we'll use since we're calculating a sample mean to estimate a population mean, and the population standard deviation is known. We divide the population standard deviation, which is 2.3 from the question, by the square root of our sample size, which is 5, because we've selected 5 people. The square root of 5 is 2.4. And if we divide 2.3 by 2.4, we get 0.96, rounded to 2 places. That's our standard error. Our standard error is 0.96. Now let's answer this question. How far should we expect the unknown population mean to be from our sample mean of 6.6? Well, since the standard error came out to 0.96, we think that the population mean is about 0.96 away from our sample mean in either direction. We can't say that it's exactly 0.96 away, but that's our estimate of how far away it is. Now let's calculate a standard error in a different situation. In this situation, a person wants to estimate the mean hours slept per night by people in a city. But in this situation, the person doesn't know what the population standard deviation equals. And the person randomly selects 5 people from the population and records their sleep times by doing a survey. Let's go through the steps of getting the standard error in this situation. First, let's actually get the sample mean. If we add the answers and divide by 5, the sample mean is 6.6. That's the average of our sample. Now, once again, we need to know if the population is 20 times larger than the sample. That's because if it's not 20 times larger, we need to add that extension to our formula, the FPC. When we divide the population size from the question by our sample size of 5, the answer does come out bigger than 20, which means that the population is 20 times larger. We can check it off, and since it's 20 times larger, we don't need that extension. We can just use the short formula. Now let's go through the actual steps of calculating the standard error in this situation. The population standard deviation isn't known. It isn't provided to us, which means that we don't know how much dispersion is in the population. So what we're going to have to do is calculate the standard deviation of our sample, which measures the dispersion of our sample, and use that standard deviation to estimate the amount of dispersion in the population. So we're going to use this formula right here, sample standard deviation divided by the square root of n. This is the formula that's used when you're calculating a sample mean to estimate a population mean, and the population standard deviation is not known. Before we can use this formula, we have to actually calculate our sample standard deviation S based on our data. So what we do is we take our 5 answers from the 5 people, we take the 5 sleep times, and we plug those into the sample standard deviation formula. To get the standard deviation, we subtract each answer by the mean. I rounded off the mean to 7 because to make the answers a little bit easier to deal with. The mean of the sample was actually 6.6, so I should be subtracting by 6.6, but I'm just using 7 instead. So we subtract each data value by the sample mean of 7, and we get the deviations from the sample mean. Next, we square each of these deviations. We multiply each deviation by itself to get these squared deviations. 1 times 1 is 1, 0 times 0 is 0, negative 2 times negative 2 is just 2 times 2, it's 4, and negative 1 times negative 1 is just 1 times 1, and it's 1. We add the squared deviations when we get a total of 6. Next, we want to get the average of the squared deviations. So to get the actual average, we would divide by 5. But since we're calculating a sample standard deviation, we do a little bit of an adjustment. We drop this number down by 1 and divide by 4. This adjustment just makes the sample standard deviation more accurate. So 6 divided by 4 is 1.5. The square root of 1.5, well, this 1.5 is called the variance. But to change the variance to the standard deviation, we have to go one step further and take the square root of the variance. And then that's the standard deviation, S. So S is 1.2. Next, we take this S of 1.2 and plug it into the standard error formula. We divide 1.2 by the square root of our sample size of 5, and we get our answer. The square root of 5 is 2.24, so we divide the S of 1.2 by 2.24, and we get 0.5. So the standard error is 0.5. So let's recap what we did. We subtracted each data value by the sample mean of 7. We got these deviations. We multiplied each deviation by itself to square them. We added the squared deviations and divided the total by n minus 1, 1 less than the sample size. The answer was the variance. 1.5 was the variance. We took the square root of the variance and got our sample standard deviation of 1.2. And that's sample standard deviation is S. Next, we took our S and plugged it into this formula. We divided 1.2 by the square root of 5 and got our standard error. I wanted to mention that when you're using this formula to calculate the standard error, and you're using the sample standard deviation as a substitute for the population standard deviation, the answer is actually called an estimated standard error. It's not the true standard error. To get the true standard error, the true standard error is what you get when you use the other formula that we used the first time, which uses the population standard deviation. So this is an estimated standard error. And how far do we expect the unknown population mean to be from our sample mean? Well, the standard error was 0.5, so that's how far we expect it to be. We expect the population mean to be about 0.5 from the sample mean on either side. Now let's go through the third example. Now we're in a situation in which we want to calculate a sample proportion to estimate a population proportion. In this example, a person is interested in estimating the proportion of people in a certain city who voted during the last election. And the city has 4,878 people. The person randomly selects 5 people from the city and gives them a survey and asks each person if he or she voted during the last election. And these are their 5 answers. 4 people said yes and 1 person said no. Before we get the standard error, let's find out what the sample proportion equals. The sample proportion is just the proportion of voters in the sample who did vote during the last election. We can get this by dividing the number of voters, which is 4, by the sample size of 5. 4 divided by 5 is 0.8, so 0.8 of the sample voted during the election. The symbol for sample proportion is p hat, so we would say p hat equals 0.8. Now we need to know if the population is 20 times bigger than the sample, because if it's not 20 times bigger, we have to put an extension on the formula. So we're just going to divide our population size by our sample size and see if the answer comes out to at least 20. We're going to see if it comes out to 20 or bigger. And it is 20 or bigger. So this number, 975, is bigger than 20. So the population is 20 times bigger. And we can just use the short formula. So this is the formula we'll be using for the standard error. First, we plug in our sample proportion, p hat, which is 0.8. We subtract we subtract 1 by p hat in the parentheses. And it comes out 1 minus 0.8 is 0.2. Next, we multiply the 0.8 by 0.2, and we get 0.16. We divide that by 5, and we get 0.3, and the square root of 0.3 is 0.02. The standard error is 0.02. Remember that this p hat of 0.8 was what we solved for in the last question. We're just taking the number we found last time and plugging it into this formula. So since the standard error is 0.02, that means that we think that the unknown population proportion is about 0.02 from our sample proportion. So the sample proportion is 0.8, because 0.8 of our sample voted. And we think that the proportion of the entire population who voted is roughly 0.02 away from 0.8. So now let's get into the next measure of accuracy, which is the margin of error. It can be calculated in the same three situations in which the standard error can be calculated. When you're calculating a sample mean to estimate a population mean, and the population standard deviation is known. When you're calculating a sample mean to estimate a population mean, and the population standard deviation is unknown. And when you're calculating a sample proportion to estimate a population proportion. Each of these three situations has its own formula for the margin of error. These are the three formulas. The second part of each formula is just the standard error. It's the same formula we've been talking about already. The only thing that's new are these confidence coefficients. A confidence coefficient is a value that's looked up in a table, and it's multiplied by the standard error to get the margin of error. So in each of these situations, to get the margin of error, you look up the confidence coefficient, and you multiply it by the standard error, and you get the margin of error. In these two situations, the confidence coefficient is labeled with the letter Z, and in this situation, it's labeled with the letter T. So that's because you actually use different tables in these situations. If it says Z, you go to a table called the Z table to get the coefficient. If it says T, you go to a different formula called a T table to get the coefficient. So when you see these different letters, just think that if it's Z, you go to one table, but if it's T, you go to a different table. Also, just like with the standard error, if the population you're sampling from isn't 20 times bigger than your sample, you have to add the FPC to the standard error. Unlike the standard error, the margin of error actually has requirements for how big the sample size has to be. In order to calculate the margin of error, your sample has to be big enough. Otherwise, you can't calculate the margin of error accurately. So let's go through those sample size requirements. If you're using a sample mean to estimate a population mean, and you want to calculate the margin of error, it either has to be that the population that you're sampling from is normal or bell-shaped, or if you know that the population is not normal, then you have to use a sample of at least 30 to calculate the margin of error. So if the population is normal, and it's known to be normal, there's no sample size requirement. You can always calculate the margin of error. But if the population you're sampling from is not normal, or if you're not sure if it's normal, then your sample size does have to be at least 30 to calculate the margin of error. If you're using a sample portion to estimate a population proportion, and you want to calculate the margin of error, this rule tells you how big your sample size has to be in order to calculate the margin of error. So you have if n times p hat is at least 10, and n times 1 minus p hat is also at least 10, then your sample size is big enough to calculate the margin of error. But if one of these comes out less than 10, then your sample size isn't big enough, and you can't calculate the margin of error. So overall, there's two situations in which the margin of error can be calculated, and each situation has its own minimum sample size that has to be met. So let's go through our first one example right here. We're in a situation in which a person is calculating a sample mean to estimate a population mean, and the population standard deviation is known. The person knows that it's 2.3. And also the person knows that the population is bell-shaped or has normal distribution, meaning most people are in the middle of the range and there's fewer extreme people at the tails. The person randomly selects 5 people from the population and surveys them on how much sleep they're getting per night. Sample mean is 6.6 again. Now we want to know if the sample size is big enough for us to calculate the margin of error. So, and it turns out that yes, it is, because if you're using a sample mean to estimate a population mean, and you know that the population has a normal distribution, then there's no sample size requirement. You can always calculate the margin of error. So let's calculate the margin of error to see how accurate our sample mean of 6.6 is. We have to use these steps. First, we go to a table to look up that confidence coefficient z. We want to calculate the 95% margin of error, which means to go to 0.95 and get the coefficient of 1.96 from the table. The table says it's 1.96. We plug that in right here, 1.96, and we multiply that by the standard error, which is just the same form that we used before. The standard error is just the population standard deviation, which is 2.3 from the question, and the sample size is 5. If we know that the square root of 5 is 2.24. If we divide 2.3 by 2.24, like I did here, I get 1.03. So the standard error comes out to 1.03 right here. Next, I just multiply this 1.96 by the 1.03, and I get the answer, the margin of error. The 95% margin of error is 2.02. Now let's make a quick diagram so that we understand what the margin of error is telling us. We have this population mean that we're trying to estimate. We're trying to estimate the mean hours slept per night by people living in the city. Remember that the symbol mu, the Greek letter, is population mean. We don't know what this population mean equals. We're trying to estimate it. And what this margin of error is telling us is that when we took our random sample of 5 people from the population, we had a 0.95 probability of getting a sample with a sample mean somewhere between this area. So remember that. So this is what the 95% actually means. It means that when we took our random sample from the population, we had a 95% chance, or a 0.95 probability, of getting a sample mean between these boundary points of 2.02 below and 2.02 above the population mean. we only had a 0.025 chance of getting a sample mean way out here, and only a 0.025 chance of getting a sample mean way out here. I'll tell you how I got this 0.025. I subtracted 1 by 0.95 and got 0.05, and then I divided 0.05 by 2. 0.05 divided by 2 is 0.025. And then that's where these came from. So these three probabilities add up to 1. Now let's look at another situation. A person is calculating a sample proportion to estimate a population proportion. The person is interested in estimating the proportion of people who voted during the last election. The person randomly selects a sample of 50 people and surveys them. 30 people say yes, 20 people say no. So let's see what our sample proportion is. If 30 out of 50 people said yes, then the proportion is 0.6. We just have to divide the number of yeses by the sample size. So 0.6 of the sample, or 3/5 of the sample, said yes. So our p hat is 0.6. Remember, p hat is sample proportion. Now we can use this rule to see if our sample size was big enough to calculate the margin of error. If n times p hat and n times 1 minus p hat both come out to 10 or bigger, then the sample size is big enough. So let's go ahead and check. N is 50. Remember, we have 50 people. That's our sample size. 50 times our p hat of 0.6 is 30. 30 is 10 or bigger. So check this off. Now we do 50 times 1 minus p hat. 1 minus p hat is 1 minus 0.6, which is 0.4. 50 times 0.4 is 20, and 20 is 10 or bigger. So check this off also. So this is 10 or bigger. This is also 10 or bigger. Since we checked off both of them, and they both came out to 10 or larger, our sample size is big enough. If one of these had come out less than 10, like if one of them had come out to 7, then our sample size would be too small, and we wouldn't be able to calculate the margin of error. But since they both came out to 10 or larger, we can go ahead and calculate the margin of error because we do have a big enough sample size. So this, I said earlier that this is the formula that's used to calculate the margin of error. When you have a sample proportion, it's the z coefficient times the standard error. And just like before, when you're calculating the 95% margin of error, the z for 95% is 1.96. This is coming right from the table. Next, we multiply 1.96 by our standard error. This whole thing comes out to 0.07. The standard error is 0.07. 1.96 times 0.07 is 0.14. So our 95% margin of error is 0.14. That's the answer. Now let's create a diagram to look at what that actually means. We have this population proportion that we're trying to estimate. The symbol for population proportion is p. So p hat is sample proportion. Population proportion is actually p. So we're trying to estimate p. And since the margin of error, since the 95% margin of error is 0.14, we know that when we took this random sample from the population, we had a 95% chance of getting a sample proportion within these boundaries around what we're estimating. We had a 95% chance of getting an outcome within 0.14 of the true statistic in here. We only had a really small chance of getting an outcome out here or an outcome way out here. When a person calculates the 95% margin of error, it gives the person some reassurance that their outcome probably did fall in this range, and it probably didn't fall way out here, and it probably didn't fall way out here. Basically, gives the person an idea of where the outcome probably fell around the true statistic. And that's all for this video.